With hypothesis tests, just like with confidence intervals, you have to justify why you're doing what you're doing. And as I said, that is just as important, if not more important, than the calculator scripting. Because I know that you know how to press the buttons on your calculator. I don't care. Your calculator is going to do it for you. Show me what you're doing and why, and communicate it on paper. That's the key to getting forward, and that's the key to acing your exams in this class. If you can do it in your brain, but you can't communicate it on your paper, you're not going to score very high. Does that make sense? Okay? You will be judged. It's not like you're taking an oral exam on the AP exam. You're going to be judged by what you put on that paper. And for the multiple choice part, it's a right or wrong. It doesn't matter how much right work you had on a multiple choice answer. If you choose the wrong choice, it's wrong. The free response is more forgiving in some instances. In other words, you can make a small computational mistake. But as long as you've supported everything, and basically if you like dropped the negative sign or you wrote the wrong t-score down instead of the right t-score down, but you carried that through the whole exam or the whole problem, you can get a 4 still. And notice that I'm not particular when I grade stuff in your class about your rounding of decimals. I do pay attention to it, correct? And I say take it to 4 decimal places. But really, has anybody ever been dinged hugely because of rounding issues? But have you dinged hugely? Yes, question?
On the AP test, do they have them round to 4?
It's specific. It'll say round to 2 or round to 4. And again, just like 95% is our general rule, if it's not stated, we'll round to 4 unless it's stated otherwise. So, and again, they are not going to be, if you rounded to 3 or 5 and the rest of your problem is correct, and they said round to 4, you probably get a 4. I would bet that you would get a 4 out of that. Because if you did everything else correct, and you didn't take it a 4 or 3, they don't really care about that. Because they know in the future, if you talk to them, oh, duh, I knew it was 4, I just put something down differently. They don't care. But they do care that you get everything else correct because you communicated your statistical knowledge. Does that make sense? Okay. So, again, this class, I'm going to ding you if you don't communicate. Get it from your head onto your paper. I'm grading you by what you write on that paper. I'm not grading you like, oh, this person really is smart. They get their answers right all the time in class. They must know what they're talking about because in their head they know how to do all this work. If you don't write it, I don't grade it. And the same works in the AP exam. I think that makes logical sense. You just might not like it because you guys don't like to write that much. So are we clear on that? Okay. So, justification, hypothesis test, chapter 10. It is going to be reinforcement of everything we did on chapter 9. Hypothesis tests complement confidence intervals a lot. It's just an extension of a confidence interval, and in many ways it's just a way of looking at a confidence interval differently. Your justifications, why you're doing what you're doing, are still the same. Independent, random, and normal. And to satisfy independence, it needs to be less than 10% of the population. And you need a sentence in there to say something like, it's reasonable to assume that it is less than 10% of the population. For example, if your sample is 32 somethings, then it's reasonable to assume that those 32, I don't know, birds are less than 10% of the population of that species of bird in the world. It's just a sentence, but you need to address it. Random, you need to address it. It is very likely that they tell you in the context of the problem. They conducted a random sample. Pretty frequently it's there. If it's not, basically you need to cite the problem. It says, study was conducted from a random sample of the bird population. A sentence telling whoever's grading your paper that you've read the prompt, you understand what the prompt is saying, and you're making a judgment based on it. If it's not stated in the context of the problem, then over here you want to say something like, I'm going to assume that the sample was a random sample so I can justify using my t-test or my t-interval. Does that make sense? We're talking about statistical validity here. And that study was conducted from and ... citing what it is you're talking about. Normality. Yeah, I am. Normality can be represented multiple ways. Way number one, if you're talking about a sample mean, an average, and the number you sample is greater than or equal to 30, then the central limit theorem says that this sampling distribution will be approximately normal. Okay? So that's number one. And we would say something like sample is sufficiently large. Sample is sufficiently large, so the central limit theorem applies. Therefore, our sample is approximately normal. Second thing that can happen, talking about a sample mean. If n is less than 30, then we need to represent or look at your data via a normal probability plot or a box plot. And you need to make a judgment on that data. You had to do that yesterday. A lot of you guys were good at that one. I think, I can't talk about it, I got people taking tests. A lot of you guys were good at that yesterday. The other thing you can do here is, if your sample is less than 30, if it's stated once again in the context of the problem that the population is approximately normal, then that is also okay to apply it. This is an or situation. And then the third one is when we're dealing with proportions, and that is n times p greater than or equal to 10, n times 1 minus p greater than or equal to 10, and that would say sample is sufficiently large, and once again you can apply the central limit theorem. It's the same as this condition here. Your sample will be approximately normal. You might make flashcards of these. Get them down. They're not going to change. You need them for confidence intervals. You need them for hypothesis tests. They are the same. Any questions about our justification pieces? Yes, we're going. There you go. All right. I'm going to look at some things here. I'm going to kind of throw a lot at you in the next 10 minutes or so, 15 minutes or so, and then we're going to kind of break it down piece by piece. This next 10 minutes, don't worry about the specific details. Just worry about kind of following along the process if you can see where we're going with it. Okay, and like I said, we're going to break it down. There's really kind of 8 steps. If you printed up your notes, those 8 steps are listed on your notes. It's called a hypothesis test. Every time you run a hypothesis test, you will basically follow these same 8 steps, top, to bottom. So, here they are. Step number 1. State the population of interest. What are you talking about? If you screw up step 1, the rest of your problem is not going to be good. Step 1, the biggest thing you're going to do is you're going to decide, are we talking about a mu, or are we talking about a population parameter? Mu, remember, is a true population mean. Capital letter P is a true population parameter or a proportion. We really only have 2. Means or proportions. Just like confidence intervals. They were means with a T or proportions with a Z. Guess what? For hypothesis testing, we're going to have means with a T or populations with a Z. Yep. Yeah, it's an H sub O. It looks like this. H-O. Okay. And then we have H-A. Those are the next 2 steps. It's an H sub O. It's called the null hypothesis. You guys have seen the word hypothesis before in other classes, I'm sure of it. And you guys even kind of looked at it when we talked about our linear regression projects. You started out with, I think this is going to happen. Then you tested it, and then you made a conclusion based on what you thought was going to happen. Agreed? Is that pretty much hypothesis summarized pretty briefly on that? Yep. Okay, here's how hypothesis test is going to work statistically, and this is where we're going to get the statistical validity here. Okay? The null hypothesis always has an equal sign with it. Okay, you might want to write that down. The null hypothesis always has an equal sign. The alternative hypothesis will be what you're trying to prove. I'll say it again. The null hypothesis, another way null is 0. Another word you might use is called the status quo. That's how things are until you prove otherwise. Does that make sense? Okay? What you know, or the status quo, how things are, until there's enough to prove otherwise. And I'm going to start using, instead of the word prove, I'm going to use the word evidence. Okay? Evidence is the new word I'm going to use. Okay? So it's like this. How many people are familiar with innocent until proven guilty? Okay. We're going to look at it in this context to kind of make sense for you. By the way, the alternative hypothesis is always going to either be not equal to, or it's going to be less than, or it's going to be greater than. And as I said, the null hypothesis always has an equal sign in it. So if we're looking at equal and not equal to, we'd be looking at greater than or equal to, or less than, or we'd be looking at less than or equal to, and then greater than. Does that make sense for our null and alternative hypothesis? Again, the null hypothesis will always have the equal sign on it. And in terms of context, do you agree if I'm setting up 2 statements, if one of my statements is equal to and the other statement is not equal to, one of those 2 statements has to be true and the other one has to be false. Either something like 4 equals 4 or 4 does not equal 4. You agree with that? There's no like gray area. Okay? If I'm looking at greater than or equal to or less than, if I'm using the number 4 and 2, 4 is greater than or equal to 2 or 4 is less than 2. One of those is true and one of those is false. Do we agree? Okay? And the same thing with the other one. One of these 2, either the null hypothesis or the alternative hypothesis has to be true in the real world. Does that make sense? Do we see it's either this or this? State the significance level, that's step 4. Talk about that real quick. Your significance level we write it as the letter A. We'll call it the alpha level. And look at this relationship. Your significance level, an alpha level of 0.05 is the 95% confidence level. Okay? I'll say it again. The alpha level of 0.05 is a 95% confidence level. When we did 95% confidence, how often were we wrong? About 5% of the time. Do we agree with that? Okay. Your alpha level is saying how often you're going to be wrong. It's hand in hand with our confidence level. Okay? Step number 5. Probably one of the most important steps. The thing that I've been talking about all day today. The thing a lot of you guys didn't do on yesterday's exam. Tell me what you're doing and why you're doing it. Provide justification as to why you're going down the path you're going. Number 6, tell me this test statistic and compute its value. Again, proportions are going to go with what statistic? Z. And means are going to go with T. So is it going to be Z's or T's? Just like our confidence intervals were, Z's or T's. This stuff, determine the p-value, reject the null, fail to reject the null. I'm going to get into that a little bit more tomorrow, but I just want to see you guys get these 8 steps down. Once again, determine the p-value. I'll talk about that. P-values, and we're going to compare that to alpha values. If the p-value is less than or equal to our alpha value, we reject. The other thing we do is fail to reject, is if the p-value is bigger than our alpha value. Okay? And I'm going to work on context. Like I said, I'm throwing a lot at you right now because I'm going to start using this over the next 3 or 4 days, and you'll have it down by the end of the 4th day. You're going to have these 8 steps memorized by the end of the 3rd or 4th day. Lastly, based on what you did in step 7, tell me what that means. Bless you. State your conclusion, citing the context of the problem, which is really like your last sentence you did when it said interpret the 95% confidence interval or interpret the 90% confidence interval. State the conclusion and the context in the given problem. Okay? That's a lot of stuff. But I will tell you that the first 5 steps of this, and even halfway through step 6, you guys know how to do already. So the next 3 chapters of our book are really steps 5 through 8. Okay? So I'm going to break it down. I'm sure you guys have a lot of questions because all I did was just give you definitions, but I want to show you how it works out. Here we go. Technology is dramatically changing the way we communicate. In 1997, which is what, almost 15 years ago, a survey of 880 U.S. households showed that 149 of them used email. Use those sample results to test the claim that less than 20% of U.S. households use email. Use the 5% significance level, and then is the conclusion valid today? Why or why not? Okay? So, for the first time ever in this class, we've now been presented with a set of data from a sample, and now they're asking us to take the information we got from our sample and make some judgment about the population. This is the whole reason, this is kind of the climaxing point of what we've been doing up to this point in this class. Sample from your population, run statistics on your population, make a judgment about your population based on your sample. Okay? So here's how it's going to look. Again, 8 steps of the hypothesis test. Step number 1, identify what it is you're talking about. Is this a proportion or is this a mean? Proportion. How do we know it's a proportion? It tells us 149 out of 880. So it tells us we're using a proportion, which in the back of your head should say at some point we're going to talk about a z statistic and not a t statistic. Okay? So, step number 1, don't use anything data-wise. You're identifying what the population is that you are studying, that you are talking about. In this case, the thing we're going to make a judgment about is what? So the true proportion of United States. True proportion, yes.
So, so this is like a preemptive this whole like 8-step process.
This 8-step process is going to be saying, if you went out in the real world and sampled 880 households about who used email, at the end of this, I could actually report out a statistically viable solution and say that I could satisfy this claim that less than 20% of all U.S. households use it, or I can't. So it's saying that these claims, like what is it, one Trident, 9 out of 10 dentists or something like that, this now is what they should have done when they report that data, and they may or may not have. It's the true proportion of U.S. households that use email. Do we agree that we don't know that statistic, or that number? We haven't gone out and asked every single household in the United States, do you use email? Right? Okay. But what we can do is sample. That's what we've done. So we're trying to make some judgment about our population. We don't know what it is. Steps 2 and 3. That is the null and alternative hypothesis, H0 and HA. H0 always has that equal sign. HA is always the other thing. HA, the alternative hypothesis, is always what you're trying to demonstrate. Okay? Do we agree that we want to demonstrate that less than 20% of U.S. households use email? So my alternative hypothesis is going to be that my population is less than 0.2. Because that's the thing that I can prove, my alternative. I actually can never prove my null hypothesis. I'll come back to that again later, but I can never prove the null. I can only have strong evidence for my alternative. It's going to come back to evidence. If my alternative is P is less than 0.2, hopefully you'll agree that my null hypothesis is going to be greater than or equal to 0.2. Does that make sense? It has to be one or the other. Step 4. State the alpha level, or the significance level, so the alpha level. It says use 0.05. All we need to do in step 4 is say alpha equals 0.05. We're halfway done with that problem. If you can't get these 4 steps correct, you can't do the rest of the problem. They're that important. These first 4 steps are easy, if you can get it from the context. Step number 5, tell me what you're doing and why you're doing it. How many proportions do we have here? How many proportions do we have here? Very good. We have one proportion. There's not 2 different things. There's one proportion. Specifically 149 out of 880. So we are going to be running a 1 proportion Z test. And if we're doing a 1 proportion z, we need to satisfy our 3 conditions: independent, random, and normal. So we're going to check for normality. How do we check for normality? What? Sample size. In this case, it's a proportion, so that needs to be n times p greater than or equal to 10, and n times 1 minus p greater than or equal to 10. So that's going to be, and I'll say normality, and I'm going to say normality slash sufficiently large. Okay? And let's see. I think we're plenty large, by the way. 149 over 880. So this would be 880 times 149 over 880 greater than or equal to 10. That's a yes. And that's 149. And then 880 times 1 minus that proportion is also greater than or equal to 10. So I can use the central limit theorem. My sample is sufficiently large, so that sample will be normally distributed. And so I'd say normality justified, sample is sufficiently large. Those are the words that I would use to describe that. Next part, normality. What else? Random. Did it say that we had random sampling in this problem? Technology is drastically changing. A survey of 880. So we're now going to have to say, assume sample was a random survey. Show that you looked into the problem and said no. It didn't say in the context of the problem. I have a red flag here. I'm concerned my answer might not match. This might not be statistically valid. I don't know if that sample's random or not. But I'm going to assume that it was random and they just forgot to tell me. Last step. Independence. Independence is justified. In this case, sample, and I'd say 880 is less than 10% of all U.S. households. Yeah.
Can you put the population of US households greater than 8,000?
Yeah, that's fine. That's independence there. Independence is justified because the sample, which is 880, is less than 10% of all U.S. households. Yeah, we've got more than 8,800 households in the U.S. Have that more now. Okay? Yes?
I'm kind of confused with step 6.
Step 6, we're not there yet.
That was part of step 5.
This is all 5. That's all step 5. That's step 5. You're probably confused with step 6 because we haven't covered it yet. For those of you guys asking where the math is, here it comes. Step 6. We're going to be using a z-statistic. Your z-statistic is p hat minus big P over the square root of p times 1 minus p over n. Like I haven't seen that before somewhere. Does that look familiar?
The bottom.
The bottom? How did we originally do z's? Wasn't it actual minus that over that? And then if we sampled it, it was that? Isn't that? That? Yes and no, but I mean, they're not exactly the same thing. No, they're not exactly the same thing. Or aren't they speaking to the same idea? Slightly? Let's look at this one. Didn't you calculate when we did this statistic? Wasn't that statistic, if that was true, and you sampled and got this, wasn't that telling you how rare that event was in terms of standard deviations? We calculated this and got a standard deviation, didn't we? I mean, got a number. That when we z-scored it, it was a number of standard deviations above or below what that was supposed to be. The example that kind of makes a lot of sense to me is that trout one. Remember that normal distribution with the trout? What's the probability that you fish into that lake and you get a trout that's more than 8 inches long when they're supposed to be 6 inches? You guys kind of remember that problem? Okay. And you calculated that probability. And based on whatever that z-score was, in terms of standard deviations, in fact, if you got a standard deviation of +3 for an 8-inch fish, that should be a very rare event. But if you got a z-score of, say, 1.1 for an 8-inch fish, you'd say you probably have a pretty high probability of actually catching an 8-inch fish in that pond. Does that make sense in context connections there? Yes? Give me a thumbs up or thumbs down if that makes sense in terms of context connections, because I need that, because that's where we're going here. Okay? That's where we were long ago in a galaxy far, far away. Here we are back in the context of this problem. Because this part is huge. Today's a big day. My p hat, that's my sample. 149 over 880. My p is from my null hypothesis. Here's the deal. My null hypothesis is what I'm assuming to be true without evidence. I'll say it again. My null hypothesis is what I'm assuming to be true without evidence. And the bottom part, we can kind of do that pretty quickly. That's 0.2, 0.8, and that's 880. All right. Everybody right now, real quick, just calculate that z-score. Should be negative. No big difference between 2.2 standard deviations above and 2.2 standard deviations below, though. Yeah, I think it should be negative 2.27, something like that. Negative 2.27 is what I'm hearing. All right. Before I start talking about that, is everybody okay up to this point? Any questions or clarifications up to this point? Yeah.
So why is that P
Why is it here?
I see. Okay.
Okay. All right. Really need to try to think about this as I speak it. So try to understand what I'm saying. Don't worry about calculations. Just kind of bird walk with me for connections about what we know to be true with the normal distribution. Think about your normal distribution. It has a mean of 0 and a standard deviation of 1. We know 1 standard deviation away is 68% of our data, 2, 95, and 3, 99, right? Okay? And what we've done with our statistic here, we said, based on this data set, this sample, p hat, is negative 2.27 standard deviations below average. Does that idea make sense? That's what the z-score means. Okay? Here's the big connection on the hypothesis test. Evidence. Remember, this is what we assume to be true without proof. Again, this is what we assume to be true without proof. If this is true, don't you think I got a pretty statistically rare sample if this is true? In other words, if 0.2 is a true, me reaching in and sampling 880 households and getting this value, it says I am negative 2.27 standard deviations below what you guys hypothesized to be true. That is a large way away, isn't it? In fact, the probability that if this is true, and you reached into that bucket and pulled out that sample, the probability that you reach out and get that, isn't that norm CDF, negative 10, negative 2.27? Isn't that the probability that if the population is 0.2, you reach in there and you get that sample that is at that event or less than that? Isn't that what that probability is? Does that make sense? So everybody norm CDF that right now for me. Negative 10 to negative 2.27. 0.012? This is normal CDF, right? If I'm asking you the probability that you reach in and get a sample that is this far away or more from 0.2. Does that make sense? So we did in chapter 6 or 7 or something like that, a while ago. You could use negative 100 if you want, negative 1,000. This is, remember, lower, comma, upper. No. No. Yeah, you can use negative 100. It's going to be the same decimal value. What do you guys get there? So the probability is 0.012. Is everybody okay with that? Okay. So the probability, let's pretend we go back to the Gatorade bucket. I said this is a big connection piece because I want you to see what's happening. I told you guys in the real world, 20% of U.S. households use email. So I sampled from my bucket. All the U.S. population, all the U.S. households are in there. I pulled 880 out. I got 149 of them out of the 880 that said they use email. How rare is it that I get that sample if the 20% is true? You've told me it's so rare that I get that sample that it will only happen 1.2% of the time. Does that thought connection make sense? Because if that thought connection makes sense, here's the closure. Since it's so rare that 1.2% of the time I'm going to reach in there and get that sample, then I have strong evidence to say what you assume to be true is wrong and that the opposite must be correct. That's your connection piece for hypothesis testing. If this is true, then we've got a really rare sample. And because I know how the normal distribution behaves, and because I've justified my application of the normal distribution up here, then I have strong statistical evidence to say, no, that's wrong. The population must be less than that. Those are the connection pieces. Do we see that thought process where I've just used about 8 chapters worth of work in one problem? Yes? Haven't I pulled a little bit from here, a little bit from there, a little bit from there, a little bit from there? But you hopefully, if you've tuned in with me in class and I've done my job right, you're seeing how these little pieces do fit together. And that's what I want. Today's the first day we're looking at this, and the next 3 chapters are all about this. Okay? This thing right here that we got, that's called your p-value. So the p-value here is 0.012. What? No, it's going to be step 7. Step 7 is determine the p-value. We just did that. Now we're going to make a judgment. Small p's means reject. I'll say it again. Small p-values means we reject. We always compare the p-value to the alpha value. The alpha value in this case was 0.05. We stated it earlier. So my p-value, which is step 7, I'm going to say my p-value, 0.012. 0.012 is less than or equal to 0.05. Again, evidence. Small p-values is strong evidence. Larger p-values, not so much. So because my p-value is smaller than my alpha value, we will reject the null hypothesis. Okay? No. 8 is going to be context. So I'm going to write up your sentence. Remember, like, we are 99% confident that it's true, like we did before. That's step 8. Step 7 is dealing with the data. Reject or fail to reject. Yes, and then
You have to put that reject or
we need to state that.
Or what would,
The other thing we would be is actually fail to reject.
okay.
So I'll talk more about the fail to reject part tomorrow, because we don't prove the null. It's fail to reject. So reject the null hypothesis. And then step 8 is putting it in context. What?
If a larger p-value is stronger, why are we rejecting it?
Not a large, small p-values.
You said the smallest.
Yeah. I don't know. Perhaps. I don't know. I'm pretty sure I said small p's means good things. All right. You might be right. I don't know. If I did say that, I'm telling you now, we want small p-values. The smaller the p, the higher the probability we are of rejecting. We are 95% confident. Notice context. State the confidence level. Put it into the context of the problem. We are 95% confident that there is enough evidence. There is enough evidence to conclude that the true proportion of U.S. households that use email is less than 20%. You.
Your name.
What?
First blank on the name.
First blank on number 8.
Is there really?
Oh, I can say, or we can say. I just read as we are.
I Jessica can say.
I, Jessica, could say with 95% confidence.
Which word?
Huh? Or question? Okay.
Will it ever
Run
be
fast.
canned?
It's a nice day to run.
Will it ever be canned?
We're going to talk about that.
Oh, that's what I was.
We're still going to get more to, yeah. There's still a lot more depth that we have to talk about. And that's a good question, but I don't think we're going to get time to talk about it today, but we will very much.
Okay, so you're never going to say like I agree because you're always trying to find what's.
The only thing we can do in these hypothesis tests is have evidence for that null, the evidence for the alternative, or not enough evidence for the alternative. Okay?
Okay.
And in the next 50 minutes as we close out class, we're going to look at the null hypothesis about innocent until you're proven guilty. Just because I failed to reject doesn't mean you're necessarily innocent.
Okay.
You couldn't you have done the crime, but I didn't have enough evidence?
Yeah.
And that's what we're going to talk about. Okay? Yeah. All right. There you go. That is your brave new step into the new world of hypothesis testing, which is statistical significance. We rejected the null. We rejected the null hypothesis. So if the null hypothesis is what we reject, and because the hypothesis we talked about, it's either this or this. There's not any in between. If there's evidence to say that's not true, then this must be true. And so what we've said is, since we rejected the null hypothesis, that's enough evidence to say that the alternative is correct. And the alternative is U.S. households that use email is less than 20%. That's our alternative hypothesis. Does that make sense? The null is that it's greater than or equal to 20%. No, the claim. It says test the claim that. So it says test the claim. I want to prove that. Okay? All right. Some summary stuff real quick to see if we're on getting the idea of this. The null hypothesis always has an equal sign. Again, it's either equal, less than or equal to, or greater than or equal to. The alternative hypothesis is not equal to, less than, or greater than. Kind of flirted with this idea earlier. You reject the null hypothesis, which we just did, or you fail to reject. There is no proving. Statisticians don't like to be wrong. So we look at things in terms of evidence. Yep. The null hypothesis is what we assume to be true without evidence. Or somebody's claiming to be true, and then I'm going to try to prove them otherwise. Yeah, because we can only prove the alternative hypothesis. And we can't even prove the alternative. We can say, we can have a lot of evidence that the null is wrong. Does that make sense? Like in the context of the last problem, if I reached in and it was 20% and got that sample, it's a really rare event. So I'm going to say that's evidence to say that your 20% is wrong. It's hard to take you seriously with your bunny ears with your little nose. All right. Once again, and you saw in the last problem, all conclusions are based on the alternative hypothesis. The alternative hypothesis is what we're trying to prove. A hypothesis test is only capable of demonstrating strong support, evidence for the alternative hypothesis. We can't do any great judgments about the null hypothesis. Okay? It's kind of like the same thing over and over and over again here. Okay? Null and alternative hypothesis work real quick, because this is what you're going to have to do on tonight's homework. Test the claim. You're basically doing the first 4 steps, I think, or 5 steps of the hypothesis test tonight for homework. Problem solved. Following problem state the null and alternative hypothesis. Part A, test the claim that population of statistics final exams, the mean score is given by mu equal to 75. Test at the 5% significance level. That just means our null hypothesis is what we assume to be true without proof. And it didn't say in the context of this problem, find out if the mean is greater, find out if the mean is less than. It just said test the mean equal to 75. So we'd look for evidence that it's not equal to 75. And that'd be an alpha level of 0.05. It's a lot of what you're going to be doing in homework tonight. Part B, test the claim that the population of sophomore college students has a mean grade point average greater than 2.25. Use the alpha level of 0.02. Your null hypothesis is going to be that the mean is 2.25. Your alternative this time, you're looking for proof that it's greater than that. So we'd look for mu is greater than 2.25. And because we're looking at greater than, then it would be less than or equal to 2.25. Does that make sense? And then our alpha level is given to us, alpha is 0.02. Yeah, we're looking for proof that it's not equal to 75. This is what, and again, we're going much deeper into all this. This is going to be a two-tailed test, and this is what's going to be called a one-tailed test because we're only looking at one side. That one we're going to be looking at two sides, but we'll get there. I just want big picture today. Good question.
So the alpha level will almost always be given to you.
Alpha level is going to be given to you. If not, you're going to assume alpha 0.05 because that's 95% confidence. All right. As I said, statisticians don't like to be proven wrong. So we will always hedge our bets. We will always kind of talk about the mistakes we're going to make before we make them so they can't call them mistakes if we told you we were going to make them. Does that make sense? So here's what we're going to do. If we're using that 95% confidence level, you guys know that I'm going to be wrong 5% of the time. Okay. We're going to look a little bit at error analysis here. I don't know if I put it in there or not. Error analysis. Let's look at this hypothesis test. The U.S. justice system. In a court of law, you are innocent until there is enough evidence to say that you are guilty. And my null hypothesis is I'm going to assume you're innocent. Remember, the null hypothesis is what we accept to be true without proof. Okay. Now in your tables, with this hypothesis test, there's two ways that we can be wrong. I want you to come up in your groups. The two ways are what are outcomes or what does it mean to be wrong in my conclusion in the context of this problem. Do you guys understand the question I'm asking? Okay, in your groups, about a minute. All right. Who can tell me one of the errors? What do we got? I heard some groups. What do we got?
Well, you could be innocent and not court someone guilty.
Yeah, you're going to need to say that better. You can be innocent but still be guilty. Not quite. Say it again.
The concept of doing a crime, like if you were on trial or something.
So in reality, in real life, you are innocent. Okay.
But you could have killed someone, but there was no evidence.
So let's think of what you got here. I think that would make you guilty.
Like they didn't know, like you knew.
No, like they were framed. They were framed. They were innocent. They were framed.
Okay, that makes a lot more
That's
sense
what
to
I
me
said before.
that
I said
you
that.
shot somebody, but
I actually said
nobody knows.
Nobody would.
I want to know what's going on inside your head.
I shot somebody, but none of you guys know except for me.
How many groups came up with, in reality, you are indeed innocent, but the court said you are, and I'm going to say outcome.
Right?
Yep.
Yes.
We call that the O.J. Simpson. How many people talk about that? The other thing that could happen, in reality,
I thought he was saying O.J. Simpson was innocent.
well, according to the court of law, he was.
Oh, I was talking about the other one, and then the outcome was guilty. I was like, I don't know.
It's supposed to be
Okay? How many people came up with these two sets of outcomes? Okay?
Is this one null hypothesis is true or false?
This is just kind of talking about things in general. Okay? And this is going to be where we're going to pick up on tomorrow. Okay? These errors the closing thought for today is this. In a perfect world, this would never happen, and this would never happen. But it's going to happen. And here's the deal. We need to choose as statisticians what error we will allow to happen more frequently. Well, it depends on the context of the problem. Here's why. If in reality you're innocent and you said you're guilty, you're going to have a lot of innocent people going to jail. But we won't have that many people that are innocent going free. I mean, I didn't say that right. Guilty people going free. Does that make sense? Yeah, didn't say it right. Now, if we're going to say we're never going to send any innocent people to jail, if we're going to say we're never going to see any innocent people to jail, then we're going to let a lot more guilty people go free because we need lots more evidence. Does that idea make sense? Okay? And that's where we're picking up tomorrow. All right, tonight's homework.